welcome back to easy concept. Shear stress across principal plane is 0. Very simple question. We know that what is a principal plane? Principal plane is a plane where shear stress is 0 and normal stress is maximum. And normal stress is maximum. So this is the this is about the principal plane and principal stresses. Okay, this normal maximum stress is called it as principal stress. Maximum normal stress, okay, is called principal stress. In nutshell, we can say in the principal plane shear stress 0 but normal stress maximum. That maximum normal stress is called as principal stress. Okay, so this is the important point. Now maximum shear stress plane, principal stress either principal stress not 0. See, principal stress is maximum, shear stress is 0. But the vice versa is not true. That means the shear stress is maximum, the principal stress is not 0. Not necessarily 0. The principal stress not 0. It may be in between some value. Okay, some value will be there. Understood? Again, I am saying the principal stress is maximum, shear stress is 0. But the vice versa is not true. That means the shear stress is maximum, principal stress is not 0. It has some value. Okay. Now, the area of shear force diagram between 2 points of span represents. So, area of shear force diagram between 2 points of a span, which it gives change in shear force between that, change in bending moment, change in load, and the change in shear force. So the answer for this question is this one. Means we know that the static equation, one is dV by dx equal to intensity of load, another one is dm by dx equal to shear force. Now take this second equation, dm by dx equal to force. So dm is equal to f into dx. If you integrate this, then you will get a moment. Okay, this is the change in moment, right? dm is what? Change in moment. So change in moment is equal to what? Area of change in shear force diagram. Change in diagram. Okay, that is change in moment is equal to change in shear force diagram area. For example, let me explain this by using a problem. There was a UDL. Let's just consider a UDL of 10 kilonewton per running meter, of span length is 10 meter. So first of all, you have to calculate the shear force. The shear force, you know, is something like a linear. 10 into 10 is the maximum value, 100. Suppose if you want to calculate the bending moment between a section, for example, bending moment at a 2 meter section. For example, I am asking bending moment at a 2 meter, first 2 meter. Then this is the shear force. This is the shear force diagram. This is the bending moment diagram. So they are asking what is a bending moment at this point. Bending moment at this point corresponding this section is area, that is change in area of shear force diagram between these two sections. Change in area. Okay. So now area between these two is what? You can calculate this ordinate. This is 2 meter, right? Therefore 10 into 2, 20. Now what is the area? We can write this is 1 by 2 into 2 into 20. So since this is 20, which is equal to 20 kilonewton meter. Therefore, this area which gives this point bending moment, this is 20. Suppose if you want to calculate for next 2 meter distance, this 2 meter distance, this is the 2 meter. What is the bending moment at this point? So bending moment at this point, that is a change in value. This is 20. This change in bending moment is equal to this change in area. Okay, so this change in area, you have to calculate this change in area. This area, you will give this value, this delta x, this delta y. This delta y is this area of this trapezium, and this 20 already you are having this 20 which comes here. Therefore 20 plus this change in area, you will get a total moment at this point. Okay, in nutshell we can say area of shear force diagram. Consider this first part. Area of the shear force diagram between 2 points. Between 2 points means the starting point and this end point of a span represents the change in bending moment between 2 points. Change in bending moment between 2 points. This point and this point. Here bending moment is 0. Here bending moment is 20. So it gives the change in bending moment. So a change in bending moment between the 2 points. Okay. I hope you understood. Okay. Similarly, I can write one more point from this equation. That is dV by dx equal to intensity of flow. Actually, here I take F, therefore this also you have to take F only. Change in shear force. Shear force represented F. Therefore, change in shear force equal to what? Area of loading diagram. So we can write this change in shear force, change in shear force between 2 points, change in moment between 2 points, right? Between 2 points. Between 2 points is equal to what? Is equal to area of what is W into dx? Loading diagram. In the same example, if you want to find out the change in shear force at this point, then you have to take area of this loading diagram. This is the rectangle, right? 10 into 2, you will get a 20. That's a simple concept. Okay. Okay, next question is the maximum shear stress is equal to, first one, a sum of the principal stress, sigma 1 plus sigma 2 or sigma 3, principal stresses. Difference of the principal stress, sigma 1 minus sigma 3, no. Difference of half of the principal stress, yes, this is correct. Half of the principal stress. Half of the sum of the principal stress, no, this is not correct. Therefore, your option is C. Okay. So I want to explain some more things about this principal stresses and principal stresses, because in the last exam 2012 also so many questions which has come from this principal stresses. Here also so number of questions has come. So I'm going to explain some of the points from the principal stress. That is enough to attend a 2 more question or 1 more question in a TRB upcoming exam. Okay. I'm going to teach, there are 4 cases. So we will see first one, case number 1. Case number 1. The case number 1, there was a stress, axial stress sigma x and sigma x, which is acting. Okay, here what is the normal stress sigma n on a plane which is inclined theta, on a plane inclined, okay, with respect to major principal plane, or we can say principal plane theta. Sigma n is equal to sigma x cos square theta and tau is equal to sigma x divided by 2 sine 2 theta. Okay, now tau max also you have to keep in your mind. Tau max is equal to sigma x divided by 2. Okay, sigma x divided by 2, that means when the sine 2 theta is equal to sine 90, that means 2 theta is equal to 90, then this sine 2 theta becomes 1. So tau max will be occur when sine 2 theta is equal to 1. That means tau max is equal to sigma x divided by 2 occur at 45 degree with respect to major principal plane. Okay, so here in this case, this is sigma x, also call it as sigma 1, is a principal stress, also called as sigma 1. Why? Because in this plane there is no shear stress is acting. Because there is no shear stress acting, we can call it as this is the principal. We are call it as this is the principal plane. Okay, so this is the case number 1. Now we are going to see case number 2. Case number 2. Now this is the biaxial stress is acting. There was a element where there are two stresses are acting, sigma x and sigma y, and this also sigma y. Okay, and here these two planes we are call it as this plane and this plane. These two planes are called it as principal plane. Why principal plane? In these two planes there is no shear stress is acting, that's why. So therefore we can say this is also call it as sigma 1. We can take it as sigma 1. This is we can call it as sigma 3. This is we can take it as sigma 3. This you can take it as sigma 1. Okay, we can take it as sigma 1. Okay, sigma x. Now we need to find out what is the normal stress and shear stress at a plane with respect to major principal plane. This is the major principal plane theta. Okay, now in this case here this is the normal stress which is acting sigma n, and this is the shear stress tau. The similar manner here sigma n will be there, so here shear stress will be there. Now here there are two normal stress, sigma n1 which is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cos 2 theta, and sigma n2 which is equal to sigma x plus sigma y divided by 2, here positive here negative, sigma x minus sigma y divided by 2 cos 2 theta. This is sigma n1, this is sigma n2. Now we can write this is, there was a relation sigma n1 plus sigma n2 which is equal to sigma x plus sigma y. Okay, or we can call it as this is what, sigma 1 sigma 3. Okay, is equal to constant. Very important examination question. Constant. These two are the normal stress at any plane. These two are the normal stress on the principal plane. We can write this is normal stress on stresses on any plane. These two are the normal stresses on normal or principal. Stresses on principal plane. On principal plane. So this you have to keep in mind. So this is important. Next one is we are going to write tau x. Okay, or the shear stress, which is equal to, we can write sigma x minus sigma y divided by 2 sine 2 theta plus tau is sine 2 theta. Sorry, this is the correct. Tau is equal to sigma x minus sigma y 2 plus sine 2, sorry, into sine 2 theta. Now, tau max occur, same as the first case. Tau max occur at 45 degree or at 45 degree or 135 degree. Okay, this tau max, which is equal to now sigma x minus sigma y divided by 2, or we can write sigma x equal to what, sigma 1 minus sigma 3 divided by 2, and these two are called it as what, radius of Mohr circle. They maybe ask you the question, radius of Mohr's circle, and here this also call it as radius of Mohr circle. A radius of Mohr's circle. So this also a question. Okay, in the case 2, important point is this. Now under that, the next important point is, okay, normal stress on the plane of maximum shear stress. I said on the maximum shear stress there was a normal stress. The normal stress won't be 0. Okay, normal stress on maximum shear stress plane sigma n is equal to sigma x plus sigma y divided by 2. Now next one is resultant stress on the plane of tau max. On the plane of tau max. Okay, tau max in the sense what, maximum, on the plane of maximum shear stress. Maximum shear stress, that is sigma r, which is equal to square root of sigma x square plus sigma y square divided by 2. Okay, next one is important point, angle of inclination of a resultant stress with the normal plane of tau max is 5. Now tan phi is equal to tau max by sigma n. So meaning this is the thing. This is the phi. This is sigma n. This is tau max, and this is sigma r. So tan phi is equal to opposite side divided by adjacent side. Okay. So now If you simplify this, this is sigma x minus sigma y divided by sigma x plus sigma y. Okay, this is the tan phi. Another relation is we can write sigma x by sigma y, which is equal to 1 plus tan phi divided by 1 minus tan phi. So this is your answer, 1 minus tan phi. Understood? Now we can go for case number 3. Case number 3. So that is, there was a element. In that element there are two uniaxial forces are there. This is sigma x, sigma y, sigma x, sigma y, and there was a shear stress. There was a shear stress. Now this is, we can take it as a tau. This is tau. This is tau. This is tau. Now in this case we can say this plane is not a principal plane. Why? Because there is a shear stress. Therefore sigma x not is equal to sigma 1, sigma y not is equal to sigma 3, sigma 1 is not is equal to sigma 3. Okay, now from that we understood the first two cases, the principal stress and principal plane, that is a sigma x is the principal stress and the corresponding plane is the principal plane in the last two cases. Since there is no shear stress is acting on this plane and this plane. Okay, so that's why we said that is a principal plane, but here you can't say this is the principal plane. Why? Because there is a shear stress is acting. So this is not is equal to sigma 1. So here first thing is you have to calculate sigma principal stresses. Okay, so before that we can write normal stresses, sigma n1 and sigma n2. What is sigma n1? Sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cos 2 theta plus tau sin 2 theta. N2 sigma x plus sigma y divided by 2 minus sigma x minus sigma y divided by 2 cos 2 theta minus, here all are positive, here negative, sin 2 theta. Now sigma n1 plus sigma n2, we can write sigma x plus sigma y. Yes, sigma n1 plus sigma n2, which is equal to sigma x plus sigma y. We can write it, which is equal to sigma 1 plus sigma 2, normal stress. Okay, which is equal to constant. This also a constant time. Now what is a tau? Shear stress equal to minus sigma x minus sigma y divided by 2 into sin 2 theta plus tau cos 2 theta. Be careful, this is cos, sin then cos. Okay, sin 2 theta plus tau cos 2 theta. Then angle of principal plane, where the principal plane is there. In the last two cases directly we have written the principal plane. That is, this is the principal plane and this is the principal plane. But here we need to first calculate the principal stress, then we can go for principal stress. So the principal plane calculation. So we can go for next slide. Now the principal plane determination. Principal plane. Principal plane. And the principal plane, what is the shear stress? 0, right? Therefore, you have to substitute the values in this equation. Shear stress equal to 0. You will get tan 2 theta p, which is equal to 2 tau divided by sigma x minus sigma y. here theta P1, which is equal to theta for first principal plane, and second principal plane is equal to theta plus or minus 90 degree. So this also important. Now you got it, theta is equal to this. You have to substitute this theta in your normal stress equation. If you substitute this, theta is equal to principal plane theta. So this is equation number 1. Substitute theta P in equation 1, we get principal stress. We get principal stress. So what is the principal stress now? Sigma 1 or sigma 3, which is equal to sigma x plus sigma y divided by 2 plus or minus. Plus means sigma 1, minus means sigma 3. Okay. Sigma x minus sigma y divided by 2 the whole square plus tau square. Okay. So this is the formula. Now maximum shear stress occur at theta is equal to theta P plus 45 degree. This is the very important factual data. You can expect a question. The maximum shear stress is occur theta P plus 45 degree. But in the case of 1 and 2, first case and second case, maximum shear stress is occur at 45 degree. Okay. Now tau max is equal to, we can write tau max is equal to square root of sigma x minus sigma y divided by 2 the whole square plus tau square. Okay. Or this is in terms of given stress, or tau max, one more formula you are having, that is these two, sigma 1 sigma 3. Okay. So that is sigma 1 minus sigma 3 divided by 2. That also gives the maximum shear stress. Sigma 1 minus sigma 3 the whole divided by 2. Okay. Now these two are called as what? Tau max, radius of Morse circle. Tau max means what? Radius of Morse circle. Understood that? Now case number 4. The last case that we are going to see, only there was a shear stress is acting. A element which is subjected to only shear stress. Then this is, we can take tau. Okay. Now in this case, what is a normal stress? Sigma n1 is equal to tau sine theta. Then sigma n2, which is equal to minus tau sine 2 theta. Then shear stress is equal to tau cos 2 theta. Then angle of principal plane is equal to theta p is equal to 45 degree or 135 degree. Then principal stresses at that point, at that plane, principal stresses sigma 1 is equal to tau, sigma 3 is equal to minus tau. Very important. This means, in nutshell, we can write sigma principal stress is equal to sigma 1 or sigma 3 is equal to plus or minus tau. Then what is a tau max? Tau max is equal to tau at theta is equal to 0 degree. At theta is equal to 0, tau is equal to what? Tau max equal to what? Tau only. Okay. So tau only. Now this is called it as a radius of Morse circle. Okay. So here in this case, the principal stresses and the tau max, everything is same. Principal stress also tau. tau max also tau. Okay, therefore here the principal stresses, normal stresses is the principal stress, right? Principal stresses, normal stresses, shear stress, everything is tau. Very, very important points. Okay, so with that we having seen the important points regarding the principal stresses. So these 3 slides is enough for your examination perspective. You have to go through this 3 to 4 times. That is enough. You can able to attend a question. Okay, this is about the question and related to that. Now we are going to see the next question, that is angular twist in a solid circular shaft of diameter d and length L subjected to torque T is theta. So there was a shaft. There was a shaft of length L subjected to torque T. Angular twist in another similar shaft of half of the length. So another similar shaft they said. That means they are made up of same material and subjected to same torque. The torque is same but length is equal to L by 2. Then angle of twist they are asking. We know that T by IP C theta by L, and they said same torque, the same size, therefore IP also same. C theta by L, this is L, but length is changing here, and C also constant. So here we can write T is directly proportional to L. Therefore theta is equal to constant in L. That constant is equal to what? That constant is equal to T divided by IPC. T divided by IPC, that is the thing. Therefore we can write theta 1 by theta 2, which is equal to L1 by L2, right? Now theta 1 by theta 2, which is equal to L1 is L divided by this is 0.5 L. Cancel out these two. They are asking angle of twist in similar shaft of, that is theta 2 they are asking, right? Therefore theta 2 is equal to 0.5 times the theta. Theta is given for theta 1 is equal to theta 2. Since they given theta 1 is equal to theta. So the answer for this question is theta 2 is equal to 0.5 theta. Answer for this question is, we can take it as B. Okay. Next question. In a thin walled T section, the shear center is located at the point as shown in the figure below. They are asking the shear center. Okay. So before that, let me explain about the shear center important points. Shear center important points, so that you never miss a question if the question is coming from shear center. 1 minute. Shear center. So about shear center, let me write 1 or 2 points. First point, shear center is a point where the resultant shear stress is acting. Shear stress or force is acting. This is the first point. Second point, this point they will ask directly to your question. Okay, next one is, if a point load is acting on the shear center, then the beam only subjected to pure bending moment and no torque and no twisting. So these two are the two important points. Okay, see about shear center. Next one is location of shear center. How to locate? Location of shear center. So they will ask you this, shear center. In that first point, point number 1, if a section is axis of symmetry about two axes, about axis of symmetry about two axes, then shear center acts at its centroid. Shear center acts at its centroid. So this is the, for example, a rectangle square section. This square section is axis of symmetry about both the axes. So now this is the centroid point, G point. The shear center also lies on the same point, that is S. Okay, this is the shear center point. For example, a rectangular section. For rectangular section, this is the shear center, and this point G is a centroid, and this is the shear center. For example, there was a I section. There was I section. And this also symmetrical about two axes. Is symmetrical about two axes. That is, this is G. Okay, and the shear center also lies on the same center of gravity or centroid. This is about first point. Now we are going to see second point. Second point, if a section made up of two linear rectangle, then the shear center lies the meeting point of two rectangles centroidal axis. See this one. For example, there was a T section. The T section is made up of two linear rectangle. Now where the shear center lies? Now the shear center in this case lies, the centroid of first segment goes something like that. Centroid of second segment goes something like that. Now the meeting point is what? This one. This is the shear center point. Suppose there was a section, that is L section. There was a L section. In that L section, this is the shear longitudinal axis of the first segment. This is the longitudinal axis of the second segment. These two are meeting somewhere here. Therefore, this point is called as the shear center. So 2 points are over. Now we are going to see some other points. Third one, for a channel section, the shear center lies somewhere here. Okay, this point is the shear center. Lies outside the C section. Okay, lies outside, and this value, okay, and this value shear center is equal to B square H square T divided by 4I. So from here to here, this is B, and this distance is H, and this distance is, this is the thickness. Okay, the fourth one, we can say C section. For C section, also the shear center lies somewhere here, and here the shear center is 4R by 5. And the fifth one is for something like that section. A small opening is there. Okay, a small opening is there. So here is the shear center. This is the shear center point. Shear center is equal to 2r. Okay, from this. Okay, small opening. So here you have to just keep in your mind, for channel section where the shear center, for a C section where the shear center, for something like that section where the shear center. Okay, and the value also you have to keep in your mind. Okay, now you can answer this thing. A thin wall T section shear center is located, is a T section. The shear center is located where? This point, right? This is the center of first segment, this is center of second segment. Okay, for this case this is the shear center. Here they marked, this case they marked here, this case they marked here, this case they marked here. Therefore these three are wrong. Option A is correct. Okay,